so we still have a little bit to cover here, okay? So a few things, okay? These hypotheses are always about the population. All right, remember that. Hypotheses are always about the population. They are never about a sample. So you will always use P and never P hat. So never about the sample. So you will never see, never put P hat in a hypothesis. The null will always have an equal sign. Okay. And then the alternative, whatever number appears in the null will appear in the alternative. Okay? So if it's 0.03 there, the alternative will also have 0.03. Always use the same number. Somebody left me a smiley face, that's nice. Okay. All right. So those are rules about the null and alternative. Now we'll cover this in more detail later on, but in the alternative. So the null hypothesis, let's say, is P equals 0.03, okay? The alternative could be, there's three possibilities. P could be not equal to 0.03, or the alternative could be that P is less than 0.03, or the alternative could be P is greater than 0.03, okay? In all of these, the null hypothesis is still P equals 0.03. Okay? Which one you choose depends on how the question is phrased. Okay? You'll see some examples in the book, and we'll talk about this in more detail in a couple weeks here. Okay? Which one to use depends on how the test is worded. Okay? And you'll see some examples in the book. Okay? If it says that the alternative is less than 0.03, okay? Let's say you draw a line, because in the center wave we put 0.03, right? And then in our data maybe it showed 0.035 or something, okay? Wherever you draw that line, the less than means you are looking for the area this way. Okay, you're always going to, less than means you're looking for the area this way. When P is greater than, okay, again, this thing goes in the middle, you draw your cutoff line. Greater than means you're going to the right. Okay. So whether the cutoff line is to the left or to the right or whatever, it doesn't matter. Less than means you're going for the left. Greater than means you're going for the right.
What about not equal to?
Not equal to, yeah. That's the last one, okay? So the last one means, this is probably the trickiest. Not equal to means go away from the middle. Alright? So in this case it means going in this direction. And then make a mirror image and do the same over here. Okay? So it says draw your cutoff and find the thing away from the middle, and then make a mirror image for the other side. That's what we do for not equal to. Okay? So this is so basically, in this scenario, you're just going to find the area over here, just like we did earlier, and then what do? To mirror it, you just multiply it by 2. That's all we're going to do. Okay? So we find this area over here, and then to make the mirror image, you just multiply it by 2, because it's going to show up on that side and then show up on this side.
What number do you multiply by 2?
The area, how much is in this tail?
Yeah.
Okay, so the area in the tail. Okay, so here the p-value is just the shaded area. Okay, the p-value is just the shaded area for all of these. So over here, find a z-score, find the area to the left. Just use what's in the table. Over here, z-score, find the area to the right. So use what's in the table and subtract from 1, or do the inverse trick, or the mirror trick. And then over here, find the area in the tail, but then you multiply by 2. Okay. You'll have a few examples of those in your homework to kind of give you some practice there. And then we'll talk about it in more detail in the coming week. Alright, we have one more thing, and this is hypothesis tests, but now we are dealing with 2 samples. Okay, it's done pretty much the same way as the other hypothesis tests. It's just the way we calculate the standard error or standard deviation changes. Okay, so this is hypothesis tests. For 2 samples. Okay, and again for proportions. Next week we're going to learn hypothesis tests for means. Okay? Using means of samples. But right now we're all doing proportions of samples. Okay. Just a quick check of our understanding. What kind of data are we dealing with when we're dealing with proportions? Numeric data or categorical data?
Categorical?
Categorical data. Categorical data, right? Because what are the proportions? What kind of examples have we used? We said the proportion of defective parts, right? Defective parts is a category, okay? Or the proportion that is germination rate, right? The seed germinated or it didn't. These are categorical variables. If you finish the class and you can't tell the difference between a categorical and numeric variable, I will be very sad. Because you probably won't have. Okay. So anyway, we're dealing with proportions, still categorical data. And this time, we have 2 samples. And so, here we're asking, do their respective populations have the same proportion or not, okay? So sample 1 represents population 1, okay? Okay, sample 2 represents population 2. In sample 1, we observe one proportion. In sample 2, we observe another proportion, okay? So from sample 1, we have a sample size, and that's going to be N1 to indicate that it's the sample size of sample 1. And it gets a proportion, and that's going to be P hat 1. And over here, we will have what? N2 and P hat 2. And the question is, based on what I see from P hat 1 and P hat 2, does that mean the respective populations, do they have the same value? So the question is, so population 1, what do you think the letter represents its proportion? So not P hat 1, but P1, right? So we want to know, are P1 and P2 equal? Okay. So a silly example could be, do men and women, do the same proportion of men have piercings as women? Okay. So the answer is no. All right. More women have piercings than men. Okay. Whether we're talking body piercings or ear piercings or whatever. Okay. More women have piercings than men. Okay. That's just statistical fact. All right. But we can, if we weren't sure about this, we could take large samples. Okay. Or we could take samples and compare the two. Okay. So here's an example. Do the same proportion of men and women have piercings? Okay, so in this case, P1 and P2 represent what? P1 is the proportion of, let's say, men. What? Proportion of men in the population with piercings, okay? Okay, and then P2, same thing, but for women in the population with piercings. I have no idea what these proportions are. What proportion of women do you think have piercings? I have no idea. Okay. I have no idea. I have no idea.
Yeah?
Okay, so let's say we took sample 1. So what would sample 1 be? Sample 1 is a random sample of men, right? Okay, let's say men, and how many of them had piercings? I'm just making up numbers. Let's say 10. Who cares? Okay. Alright, sample 2. Random sample of women. Sample of women. Alright, and let's say we found 60. Let's change this number. 50, and how many of these women had piercings?
45.
Okay. Let's just say 40. Okay. There's probably more than that, but whatever. Okay. Random sample. Okay. So based on this, do we have evidence that the proportion with piercings is different? Okay. So in this case, what is my p hat? My p hat over here is what? 10 over 60. 0.1667. And over here, p hat 2, I should write. P hat n1, n2, p hat 1, p hat 2. 40 over 50, 0.8. Okay, so these are ridiculously different, okay? In a real problem, they won't be this different, okay? So this is what our data shows. Our null hypothesis, whenever we're comparing two proportions, this is always going to be our null hypothesis. It's going to be P1 minus P2 should be what? It's that the difference between P1 and P2 is 0, that there's no difference between P1 and P2. Okay? Or we could also write P1 equals P2. Alright, but I think I prefer this. Okay, these are both saying the same thing. This one says P1 is the same as P2, and this one over here is saying there is no difference between P1 and P2. Yes?
Is the question for two sample hypothesis, is it always going to be our P1 and P2 equal? Or is that
Yes.
Oh, yeah.
At least in this class, okay?
Okay.
If you take statistics later on, they might do more complicated ones, okay? But in this class, we're just going to have the question, if you got two samples, are they the same or not? So the alternative, okay, let's say the alternative is that someone says, well, women have more piercings. Women have more piercings, or more women, the proportion of women with piercings is higher than the proportion of men with piercings, okay? So in that case, what would I write? I would write P1 minus P2 is, this represents what? Women, this represents men, so if more women had piercings than men, this would be less than 0. Thank you. That's what we want to know. So if the null hypothesis were true, anytime I take two samples and I calculate the difference between these two samples, I expect that difference to be close to 0. That's what this null hypothesis says. Okay? What we actually observe, our observed difference between proportions, our observed difference is what? It's P1 hat minus P2 hat. I'm expecting a difference of 0, but what I'm really getting is 0.1667 minus 0.8. I'm getting a difference of 0.6333. Okay? Of negative 0.6333. Okay? So this is actually really, really big. So our numbers might seem very extreme in this case. Okay? Alright. And so we would draw a picture. Yes.
Do we use, so we can use p hat in this kind of hypothesis?
No, so this is just calculating our observed difference. In the
Oh.
hypotheses, there's no
Oh,
hats, right? The
statements.
hypotheses are still statements about the population, and there's no hats in the hypotheses. what we observe, this is just coming from our data. Maybe I should have written it in a different section, but okay. So if I were to draw this picture, I'm expecting a difference of 0 between P1 and P2. Okay, when I took my samples, I didn't observe a difference of 0. I observed a difference of negative 0.6333. Okay? And I want to know how much is over here. So what do I have to do? I would get a z-score, and I would do this minus this divided by the standard error, okay? And this is the only ugly part of this situation, okay? The standard error, the standard deviation, is just an ugly formula. There's nothing we can do about it. It's just ugly, okay? And you're just going to punch in numbers to get the standard error, or standard deviation, okay? So the standard error in this situation, okay, is p hat times 1 minus p hat times 1 over n1 plus 1 over n2, okay? Where, alright, p hat is equal to total success over total observed. Okay? So it's just an ugly thing, okay? You can't, there's nothing we can do, this is just what we have to do, alright? So you just kind of have to accept this. And everything will be okay, okay? Once you accept this, yeah, then we'll go on, and life is not so terrible, okay? So let me explain each of this once you get all of this written down. Okay, so let's start over here. P hat is equal to the total success over the total observed. So over here we're looking at our data, and we want to know the total number of people with piercings. So in our case, it's total people with piercings divided by total observed. Alright, so how many people total had piercings? 50, right? I just did 10 men with piercings plus 40 women with piercings. And how many people total did we observe? 110. 60 plus 50. Okay, so I just get 50 divided by 110. And what is this? 0.4444444? I don't know. No, 0.5050? No. I don't know. Okay, 0.4545. Alright, so that is my p hat. And we're just going to use that in here. Okay, so p hat is going to be 0.4545 times 1 minus 0.4545. What is n1? 60 plus 1 over n2, which is 50. Yeah, 1 over n1 plus 1 over n2. That's just the ugly formula that we're using, okay? I mean, I could explain, but I think there's no need to, okay? We're just going to say this is the ugly formula, and we're just going to do this, okay? All right. So, all right, calculator check. I will punch this in.
Lobster. Do you like lobster? Do you like lobster?
Okay. On the inside, I get square root of 0.00909, and
the answer is 0.0955. No, 94.
Okay. Did we get that? 0.09535?
What if we have 4 decimal places?
Okay, that's good enough.
Yeah.
0.0953, and then I think it rounds off to 0.0953.
Yeah.
Okay.
It's gonna be 0.095.
Alright, you guys got that?
I do.
Check your calculators. 0.09535.
1 divided by, yeah?
Okay.
Do I do
So
plus
once
or
we
no?
have that, we can get a z-score, okay? So my z-score
1 divided by
is negative 0.6333 minus 0 divided by that 0.09535, and I get, because this is the mean,
negative.
right? This is my cutoff, and my mean is 0.
Something's wrong.
Something's wrong?
Yeah.
Okay.
What do you get?
I'm getting the 6.64.
Yeah, no, that sounds correct.
Not
Yeah.
for the z.
Negative 6.64.
Yeah.
Right? Okay, so I get negative 6.64. I get a z-score of negative 6.64. Okay, before we talk about negative 6.64, where did this 0.6333 come from? Do you guys remember where did this come from?
That is the,
Oh, we did negative.
that is the difference between P1 and
It's the observed difference of P1 hat minus P2 hat, okay? This is a very common thing that people forget. Where did negative 0.6333 come from? Remember, this is P1 hat minus P2 hat. And where did P1 hat and P2 hat come from?
From the
Yeah, these are our sample proportions. Okay, these are our sample proportions. We take the difference between our sample proportions, and that gives us basically our cutoff. My mean is always going to be 0, and then this 0.09535, where did that come from? That was just the ugly standard error formula, okay? And there's a lot of stuff involved in that. Okay, so my z-score is negative 6.64, okay? If you go to your z-table, the most negative number is like 3.49 or something. Or what is it?
it's 3.49.
Yeah, 3.49, right? Okay. And here we said something like 99.7% of the data is within 3 standard deviations. Here I'm 6.6 standard deviations away from mean. I'm ridiculously far away from the mean, okay? So it's actually, so this picture is actually not accurate. It's more so like, I'm like way out here and I'm asking how much is in the tail. So the amount in the tail is practically 0, okay? It's off, this is where the phrase off the charts comes from, okay? You look at your Z chart or Z table, and 6.64 is not on the chart, okay? We are off the chart. And so this is so extreme that we don't have values in our chart, okay?
So what do you do
or
after
table.
you find the
So
table?
our p-value, it's not 0, but it's practically 0.
Professor, should I start the list for the extra credit? Should I
Oh yeah. Go ahead, do that. Yeah. Say it. Thank you for reminding me. Okay. Let me just get a kind of quick count.
So I have a question. You know, we found this
Okay.
table.
Um,
Now what?
Yeah. So go ahead. Put your name. Pass it around. Don't sign in your friends or anything like that. And we'll do that. Thank you for reminding me. I want to
Okay.
reward you guys for being here.
3 points.
Because I appreciate you coming to class. All right.
Oh, we appreciate you, teacher.
All right. Yeah. Right. Right. Mutual appreciation. Alright, so our p-value is practically 0. So in this case, when our p-value is practically 0, what is the conclusion that we make regarding our null and our alternative hypotheses?
You tell us.
It's less than our alpha, whatever our alpha was. Even if alpha was 1% or 2%. So we do have evidence. When our p-value is less than alpha, we have evidence against the null. Okay? So in our case, so our p-value of close to 0 is less than alpha. So we reject the null hypothesis and we say we have evidence. We have evidence of the alternative against the null or for the alternative. Okay, we have evidence against the null, or we have evidence that the proportions are different. Is that okay? So anytime your p-value is less than alpha, you reject the null hypothesis and you conclude the alternative. So in this case it says, if I took a random sample of 60 men and 50 women and found that 16 or 17% of men had piercings while 80% of women had piercings, then I have very strong evidence that the proportion of men and women who have piercings is different. We'll make sure everybody gets to sign this thing, okay? Okay, is this alright? Another example, or no, you guys are done? You guys are sick of this?
Is there examples like that in the homework?
Yeah. Okay, so you'll have examples like this in the homework. Okay, so I guess we'll end there. Just make sure you sign the bonus attendance sheet, and then you guys can go.